Okay, so say you're like me and you wonder idly to yourself what exactly it is that black holes are. You wonder how they work. I mean, really, what could a black hole even be? So let's take a look at how scientists currently think that black holes are made. So, first you start with a star. Hello, star. This star is young. It's healthy with its nice yellow glow. I mean, it's like our star after all, and things have been going fairly well over here for us. But I mean, stars grow old. Stars can die. Some just collapse their layers and end up shrinking into little neutron stars. But like I said, even those stars can grow old. A neutron star is incredibly dense, don't get me wrong. We're talking densities on par with crushing Mount Everest into a marble. But then we're continuing that scale up to an object larger than the Earth. A neutron star is the core of a collapsed star, and we know how large stars can be. So, what happens when those neutron stars die further? Well, that's where things get interesting. Some just expend their energy and become little inert balls of material that are too dense to continue nuclear fission with. And while that's cool, it's still not as cool as when a neutron star loses its stability and collapses into itself again. We now have this star, a density many thousands that of Earth's, and it's collapsing into itself, all thanks to gravity. So how does gravity work with such a dense object? And I mean, gravity is the weakest force in the universe, right? But we're talking about astronomical figures here. Literally. And even when you multiply a little portion by an astronomical figure, it's a lot. Now, I know that's not very sciencey, so let's try to break it down. Gravity itself is a relational constant in the universe. The more mass an object has, the higher the gravitational pull. Einstein's theories of relativity boil down to an idea that gravity isn't so much a force on objects as it is on space-time. An easy way to think of space-time is like a sheet pulled taut. Dense objects pull the sheet down more than less dense objects. So when you see an object in free fall, it looks like gravity is a force pulling it towards a larger mass, but according to Einstein, it's moving without a force being acted upon it. It's following the flow of space-time, which is just bent towards the denser object. Now, our sun makes a large depression, but the Earth has just enough energy to avoid falling in by moving against the flow of space. This is because the gravity of the sun is spread out over a large area. Now let's shrink that area to what a black hole uses, essentially a single point. You now have this incredible density sitting in a tiny focused point. The effect is that after you get to a certain distance, the gravity is putting too much force in, and you'd need to be traveling faster than the speed of light to escape the pull. This location is known as the event horizon. To explain it, some scientists explain that if gravity is a river, the event horizon is a waterfall. Scientists also realize that with something as massive as a black hole, their effects can be extremely far-reaching. The weak force that gravity exerts on space-time that pulls things together is magnified by 1,000 or more times, and for that reason it is assumed that the center of galaxies can contain supermassive black holes that hold the entire galaxy together. These entities are dense enough and contain enough matter that their effect on spacetime is far-reaching enough to keep many hundreds of thousands of stars in check. Now, what keeps the entire galaxy from being sucked into this power-hungry creature then? Possibly nothing. We can rest easy though, as the effects of gravity get relationally stronger the closer you get. If you're interested in the math behind exactly how the relation acts, look up Gauss's law for gravity. Basically, we've got quite some time before we need to worry about escaping the powerful jaws of a supermassive black hole. So as you can see, gravity may be the weakest force, but astronomy will always show you that even the most unlikely situations can be impressive when given almost limitless potential.